to our video series. This is the first edition where we'll be looking at elements, atoms, and molecules, more specifically how to draw Lewis structures of them, and then therefore determining their molecular geometry. For this example, we'll be using our checklist, which was compiled to help you realize where your bonding electrons are, and in the end, your overall molecular geometry. So for this example, we'll look more specifically at the xenon tetrafluoride compound. And now looking at this, we can go to our checklist and start ticking off the things to do. So firstly, we need to find the total number of valence electrons. So this example will have xenon and fluorine like so. The xenon, if we refer to the periodic table, we know is in group 18, and therefore has 8 valence electrons left over. Fluorine, we know is in group 17, and therefore we'll have 7 valence electrons. Since we want to find the total amount of valence electrons for this compound, we then sum these values, and keep in mind, since we have a tetrafluoride system, we must times this value by 4 to give us a grand total of 36 valence electrons in xenon tetrafluoride. Now that we've got the total number of valence electrons down, we can now go on to drawing the main skeleton. And to do this, the rule is that you put the least electronegative atom in the center. Now, again, looking at the periodic table, we know this is xenon. So we'll put xenon up here. And we can assume that the fluorines will fall around it in a nice, even distribution, like so. And now once we've completed this, we can go on to looking at the bonding electrons that are falling in between these atoms. So I will change the color to make it more visible. But since we have bonds interacting between a fluorine and a xenon, there must be 2 electrons between each, like so. And now that we've completed the bonding electrons, we can then go on to complete the octets of these. And now looking at xenon, a complete octet of 8, 2, 4, 6, 8. We complete the octets for fluorine. And here we go. That is our compound with all the octets satisfied, except for this one, of course. And yeah, so when you add these all up, you'll notice a little anomaly here, because adding these up, 2, 4, 6, 32 valence electrons are on this drawing here. But since we calculated we needed 36 for this compound, we have 4 missing electrons somewhere. And now this is where normally in any other compound you can look to the 5th rule of our checklist, is that you can use double bonds and triple bonds. However, this example here of xenon tetrafluoride, we don't have such a case because fluorine is such an electronegative atom that it would rarely make a double bond. So in this case we can have something called an expanded octet. And this is a special case where, particularly period 3, but other examples exist, where atoms have the capacity to hold more electrons and therefore expand their octet. So what violating the rule. So here, since we need 4 extra electrons, that's 2 electron pairs. And this we can then draw on our xenon, because if you think about it, xenon in the center is the best place to hold these extra electrons. So if we draw it out again, instead of replacing the bonding electrons as line bonds, where each line is 2 electrons, include the fluorine, assuming that the octets are filled, so no need to draw them, and we can add our 2 extra pairs here. Now this atom now, in the center, has adopted a different geometry, therefore the compound itself will have adopted a different geometry. And from here, I think drawing it out in this planar manner, like so, this will make it slightly more obvious when you come to draw it and try to predict its geometry, because from here you see that if this was lying on the plane of the page, we have these 2 electron pairs above and below, and this will turn this atom in the center of the square, and we can think of this as a square planar on the page. And therefore we call this compound a square planar. Now we'll go on to a different example. And we're back. Now I'm going to give you an example you can try for yourself. I'm going to draw you the first step. And now pause the video and attempt to do the same thing as we did last time on this compound. Alright, I hope you didn't have too much trouble with that exercise. So now I'll show you how to do it, and hopefully you got the same answer. So step 1 of our checklist, we need to start adding up the valence electrons. Chlorine is in group 17, therefore has 7 valence electrons. Fluorine is also in group 17 and also has 7 valence electrons. Keep in mind that we have to times this value by 3 because we have a trifluoride system. Summing this together will give us a grand total of 28. If you got this value, we can then go on to drawing the main structure of our compound. This would go as such. Chlorine, in this case, is not the most electronegative. However, since we have dominant fluorines around it, in this case, the chlorine has to go in the middle. And when we draw our extra atoms, we can just assume the same kind of arrangement around the central atom. And now that we've drawn the main body or skeleton of our compound, we can then go on to add on the bonding electrons, which would be here. And then we can go on to fill in the rest of the octets. So fluorine, with all its octets satisfied. Alright, but here in this case we have a small problem because clearly here chlorine does not have a satisfied octet, and in fact we have 4 remaining electrons again, like in the other case. So with these 4 remaining valence electrons, which we found from doing 28 take away 24 is what the total of these valence electrons is here. We know that with these 4 valence electrons have to go somewhere, and the only place for them to go right now is on the chlorine. And the pairs will be found around about there. And yet, despite what we know about electron repulsion and trying to get as far away from each other as possible, this is the only possible arrangement given that we have hyper-electronegative fluorine atoms around the central chlorine atom. And now that we have our main body all completed, we need to start thinking about how this compound will come together in a geometrical form. So if we draw this out, again with just single bonds, for the 2 pairs here, there'll be an incredible amount of force pushing these electron pairs down onto these fluorines, making what we call a T-shape. And coincidentally, that is the name of geometrical arrangement. We call this compound T-shaped. I hope that was okay with you guys. I had pleasure in discussing this with you, and I hope you join us next time for the next video.